IASTA. And I'm Arshad Khan, and I would like to give you a brief about IASTA before starting of this lecture. So, Indian Aerosol Science and Technology Association is a professional organization for scientists and engineers working in the field of aerosol science and technology in Indian context. This association provides a platform for exchanging knowledge, know-how, resources, and information among researchers and other members. And we do organize conferences, technical meeting, lectures, and publication for dissemination of the knowledge. This organization, Indian Aerosol Science and Technology Association, was constituted by some scientists of Bhabha Atomic Research Center in 1998 in Mumbai. And currently, IASTA is having around 700 members, which includes members from academia, industry, and scientific, medical, and other parts. It is a member of International Aerosol Research Assembly, that is IARA, and Asian Aerosol Research Association, AARA. And our mission is to disseminate information concerning the development in the field through publications such as bulletin, reports, newsletter, and journals, and to organize workshops, symposia, seminars, courses, etc. in various parts of the country so as to offer a platform for all the researchers for reporting and discussing new development. So with this brief introduction of IASTA, I would like to call Dr. Tripathi for introducing our lecture speakers for the day for our monthly online lecture series. Dr. Tripathi, please.
Thank you, Arshad, and very good evening to all, and including my good friend, Professor Athanasios Nenes, which we call fondly Thanos. So welcome, Thanos, to our IASTA, monthly lecture. Professor Nenes is a professor of atmospheric processes, and is also head of laboratory of atmospheric processes and their impacts, which he calls LAPI, at the École Polytechnique Fédérale de Lausanne, Switzerland, which is also called as EPFL. He's also an affiliate researcher of the Institute of Chemical Engineering Sciences at the Foundation for Research and Technology Hellas in Patras, Greece, and a founding member of the Center of Studies on Air Quality and Climate Change at the Institute. His research focuses on the impact of atmospheric processes, especially aerosol, on clouds, climate, air quality, and ecosystems. Anybody who has probably worked on thermodynamics of aerosol must have used isoropia. And I remember when I was a postdoc at Oxford, I wrote a mail to him, and I think same day he responded and he shared the model. So this is, I think, the prime model related to the understanding aerosol thermodynamics, aerosol cloud interaction, parameterizations, and many more things. And he is the developer of this model. He is a very highly cited researcher. He is a Web of Science highly cited researcher, having co-authored 352 manuscripts with an H index of 97. Then there are many other distinctions he has brought to himself. I will just name few in the interest of time. He's fellow of American Geophysical Union. Also, he has got Copernicus Medal. He has got Triple AR, Whitby and Friedlander Award, and he has also received American Meteorological Society Houghton Award. In addition to that, he has to his credit NASA's New Investigator Award and the US National Science Foundation Carrier Award. He has by now guided 22 PhD students and 20 postdocs. Thus, we are very honored to have Thanos here. And now I hand over it to Thanos to start his talk.
Thank you so much for this wonderful introduction. And thank you so much for the invitation. It's a true honor to be here in front of this audience. And hopefully what we will discuss today will spark a discussion amongst you and possibly together. It will be wonderful to see if we can work on some of these topics together, because they're definitely of high relevance for India throughout the country and also Asia and pretty much the world. So we're going to talk about atmospheric aerosol, acidity, and its impacts. And so without further ado, let's go into the presentation. So we care about the aerosols. Everybody knows this because they can kill you. They're a leading source of premature death worldwide. Pretty much every year we have life loss that's equivalent to a COVID pandemic, and maybe even more. And a lot of this is because of the particulate matter that we breathe and their components. And for sure, there's some aspects of the particles that makes some of them more toxic than others. And so definitely acidity has a component here that we will discuss. We also care, of course, about aerosols because they reflect sunlight and affect climate. And they also can absorb radiation and also warm climates, so they have these interactions. And the amount and the composition of the particle plays a critical role on its ability to interact with radiation. At the same time, particles act as seeds to form cloud droplets and ice crystals. And so by modulating cloud properties, they can also affect climate as well. And so again, the amount of particulate matter, the size, their chemical composition, which at the heart of this acidity plays a role, can have an impact. And so just one picture here, you have many pollution sources that whenever they get incorporated into clouds and make them slightly whiter, and this is indicated by these white streaks, and these whiter regions tend to reflect sunlight and actually tends to cool climate. And that's a component of cooling that anthropogenic emissions have and affects eventually the climate sensitivity to CO2 emissions. And so again, we as a group are working very heavily on these aspects to try to parameterize particulate interactions with clouds and climate. At the same time, particulate matter can contain nutrients. They can contain nitrogen, phosphorus, also trace metals like iron and copper and manganese, and all these are very important for ecosystem productivity. Iron is the key trace nutrient that's important for chlorophyll and hence photosynthesis in the oceans. And so particulate matter can deliver these species. So again, anthropogenic emissions can perturb these nutrient fluxes, and there are very large uncertainties when it comes to the impact of aerosols mixing with pollution and affecting ecosystem productivity, hence the carbon cycle, climate, and also the food chain. So again, we will point out that acidity plays a role here as well. So before we continue, a question for the audience, and maybe many of you know the answer, but still it's fun to ask and to think about it. What really is the acidity, the pH or particulate matter in the atmosphere? And so if you actually go to a high school textbook, you usually find pH scale ranges between 0 and 12. And when we first started asking this question, the community thought that for most cases, particulate matter would be close to 7, neutral pH, maybe slightly acidic. But as it turns out, after analysis of data and exploration that took place over the last few years, we actually can have extremely acidic aerosol and all the way up to basic aerosol. So pretty much the pH scale can almost span all the possible range, and on the acidity side, actually go even further, below 0. And so this, in many ways, is a surprise, but on the other hand, it's not so surprising, actually, if you think about it. But still, this carries profound implications. So to give you an idea, in regions where you have a lot of sulfate and organics, the acidity tends to be close to 0 or 1. Yes, or -1. So that means a hydronium concentration of 10, to the 1. And so this is very high concentrations of H+. If you go to regions that are more influenced by biomass burning or dust, the pH becomes higher, so the acidity goes down. But still, aerosols can be quite acidic. And when you get into sea spray aerosol, depending on the region and the composition and the size fraction, the pH can actually go relatively high and hit slightly alkaline conditions. But still, the key point is that you have a very wide range. And to compare it to sort of things that people, get in contact on an everyday basis, your battery acid in your car has a pH of about 0. And so you are breathing particles that could have that kind of acidity. Fortunately, there are not that many of them, but still, this is the level of acidity that they may contain. Now, in India, it turns out the particles can be actually quite less acidic because of a lot of ammonia around, but still, they could be slightly acidic, and that carries important impacts. And so, getting to the point of the talk, this is about atmospheric acidity and how it interacts with particulate matter and more or less perturbs almost everything that particles can do to the Earth system. And so, when it comes to human health, particulate acidity can affect the toxicity of particles. And so, of course, if you expose particles to more acidic conditions, you will see that things get solubilized and it tends to increase the oxidative potential of these particles. At the same time, you can release nutrients more readily, make them more readily available. So that means when these particles deposit to ecosystems that require these nutrients, they fertilize them. At the same time, you can facilitate the formation of particulate matter or less. And so that carries direct impacts on the radiative balance and the particles' impact to affect clouds and climate. But at the same time, all the chemistry that goes on that may affect the amount and the particulate matter and the chemical composition of these particles are also affected by the acidity levels. So really, acidity is at the heart of everything. Now, the issue about acidity is that we have a fairly good understanding of what it is. We also have a fairly good understanding of what controls it. It's just basically a mixture of, acids and bases. And in the end, whatever sort of predominates controls if it's going to be acidic or not. And depending on the speciation, you may have more or less acidity. And that's why we understand the acidity of clouds. Again, there's liquid water that's generated from meteorology. This is a key difference between aerosols. Clouds tend to have liquid water that's generated from a process that has nothing to do with thermodynamic equilibrium. It's basically meteorology generating supersaturation, and then that makes condensable water. So that's why we say dynamics and meteorology controls the liquid water in clouds. Aerosols are a special case. The liquid water is actually in equilibrium with the gas phase, which means that the relative humidity determines how much water is in the particles. And so that is not an independent variable, the liquid water content. The humidity, once you know it, then the amount of water per mass of aerosol is kind of fixed. It varies a little bit with the composition, but you cannot have orders of magnitude difference depending on the meteorology. So this is a very important aspect, and it leads to a little bit of counterintuitive behavior of acidity when it comes to particles. But, for all purposes, essentially, you have the liquid phase, and then the acids and the bases that are in that liquid phase determine altogether the acidity levels. And so in this sense, we have a good qualitative understanding. We know what are acidic compounds that we emit in the atmosphere, SOx, NOx, VOCs that give organic acids. They tend to be acidic. And then you mix them with basic compounds like ammonia and mineral dust, which provides cations that we call them non-volatile cations to differentiate them from ammonia, which is a volatile cation. And altogether, they sort of neutralize and they determine the acidity levels. And of course, depending on the relative amount of each species in the particle and humidity, liquid water, you have the acidity levels. So in this regard, we have a very good qualitative understanding. We expect, in other words, if bases increase, the pH will go up. If acids increase, the pH will go down. The problem is that we actually couldn't really measure pH for particles. We could do that for clouds. You can collect cloud water, and if you're careful enough, you can actually stick a pH meter and get a good measurement. And those have been going on for decades. And actually, it was the basis for the acid rain, problem and developing, of course, a policy to mitigate it. Particulate matter, on the other hand, are very different. The liquid water that they have is orders of magnitude less. And if you try to collect that liquid water and then put a pH, meter in it, you perturb the system because it's always in equilibrium with the humidity. You perturb the volatiles. And so essentially the pH you would get is very different for what existed actually when it was out in the air. So you cannot directly measure pH. So to address that problem, the community has been using proxies of pH, things that could be measured that are indicators of pH. And, adopting concepts from the oceanography and, the aquatic, fields, people have been using things like ionic balances to figure out if a system is acidic or not, or ratios of cations versus anions to infer acidity. It turns out that these methods, although they're qualitatively okay, they're subject to a lot of uncertainty. And so if you're close to neutral, your measurement uncertainty basically can give you an answer that may be acidic or alkaline, so it's unreliable. Ratios as well can give you something that may be linked to acidity. In other words, if your sulfate is a lot more than your ammonium, then that ratio, if it's less than 2, indicates that you're probably an acidic aerosol. But the bottom line is that these metrics, despite, if you not consider the uncertainties, they don't really give you something that's directly linked to pH, which is really the ultimate goal. So if you can actually plot the ion balance, and this is just from measurements carried out in the field, almost a decade ago now, if you plot the ion balance against the pH, you can get a very wide range of the ion balance. Let me actually put up a laser pointer here. So this is the ion balance as calculated, the anions minus the cations. So a positive difference means that it should be acidic. A negative difference means that it should be alkaline. But if you look at, this, it's always acidic. And there's a very poor correlation between what this ion balance is and the true pH of the particles. The other problem is that the ion balances don't have the water, right? Because pH is the log of H plus concentration in the aerosol, which means you need to figure out the concentration for hydronium and then also the liquid water content. You need to take the ratio. So ion balances don't have the water content, so by definition, they're unreliable in terms of determining pH. The same thing applies for molar ratios, like ammonium to sulfate is something that's been used a lot in the community to figure out if you're acidic or not. It's a very easy thing to measure. But, again, if you take data and you plot it against pH, you can get a molar ratio that's constant and a pH that varies 1 unit or even more than that. And depending on the conditions, you can have the same molar ratio and the pH can vary a lot. So again, it's not really a strictly linked quantity to pH. So we need to figure out the way to calculate pH, and we did come up with a solution. And this goes into the thermodynamic model that was mentioned before, isotropia. The bottom line is that if you have good enough measurements to constrain a calculation of partitioning, then the models that calculate partitioning actually give pH, because partitioning between gas and aerosol is very often highly sensitive to pH. So the idea we had was, well, okay, let's apply thermodynamic models. We know that they have issues. They're not perfect. But again, we don't know anything about pH. So it's much better to know something than nothing at all. And we just make sure that the model is applied to systems that we can constrain the partitioning and test the predictions. So in other words, if the model predicts a certain partitioning and the data says the partitioning is reproduced, then your pH is probably reliable, because if it's off, your partitioning would be very off in a way that would bring disagreement with the measurements, okay? So we use the Isotropia. Other groups have been using other thermodynamic models. Bottom line is, if you use a good thermodynamic model, you can actually get an idea about the pH of particles. And so we tested this idea by using, for the first time back 10 years ago, using a comprehensive data set of aerosol composition, gas phase composition, as well as humidity in liquid water. And this is all outlined in a paper by Hongyu Guo back in 2015. This is working, of course, in collaboration with Rodney Weber at Georgia Tech. The idea is you put in the model everything that you know about the inorganic ions, gas phase, ammonia, nitric acid if you have, and then you actually put relative humidity. You calculate liquid water content. You also calculate pH. And the idea is, if you have measurements of partitioning, and if you're lucky and have also liquid water measurements, you can test the model. And so if you get good agreement, that means that the pH is reliable. And so we did this. And again, this was a remarkable study at the time, because it was really the first time we really tested the partitioning, with excellent measurements. And I'd just like to point out that, this is a period of a month, maybe a little bit more. And the ammonia levels in the Southeast US during the summertime, can vary quite a bit. The orange trace, the red trace, depending on how you interpret colors, is the measurements, and the green is the thermodynamic model predictions. And what's remarkable is that if you exclude periods where there's rain, where we know we're not in equilibrium, the two traces are almost on top of each other. They're almost indistinguishable. And if you go to the one-to-one plot, which is sort of the modeler's plot of truth, your predictions of ammonia are almost perfectly in agreement with the measurements. And in addition to that, the partitioning, the amount of ammonia that's in the particulate phase is around 50%. This is what this black trace is. What does that mean? It means that if there are errors in ammonia, it would actually translate to measurable errors in the predictions and the partitioning. So the agreement really shows that it's doing a good job and that the pH actually has to be right. Within some uncertainty, but it cannot be off by too much. Otherwise, ammonia would be very different. And so this diurnal cycle was observed during this time. It went from a pH of 1 to 0.5. And at the time when I was showing this, people were saying there's no way particles can be that acidic. Well, there's no way we can get predictions right if the particles weren't that acidic. And actually, it did explain a lot of the interesting aspects of SOA from isoprene that was observed during that campaign. So anyways, this was a great proof of concept that the method does work. And since then, it's been applied to many data sets. Colleagues from India and Asia, China, Japan, throughout the world actually have been applying this technique to figure out the pH in the region. And the idea is that we can now say that for many, many systems, you can use this approach to get the pH. And until there's a direct measurement around, this is really the best thing that we have at hand. And it's also fairly easy to apply, which is great. It also takes advantages of these large data sets of composition that are available. So it really allows us to basically develop a climatology of pH. And so what we end up seeing is that the partitioning of species, of course, depends on the pH and also depends on the liquid water and the temperature. So I'm just showing you here some results. Epsilon means the partitioning fraction. So 1 means that everything is in the gas phase. Everything is in the aerosol phase. And 0 means that everything is in the gas phase. So you can say that nitrate, in the summertime, with this about temperature range, when you have a pH of 0, nothing is in the particle phase. Once you get above 2 or a little bit higher than that, then a good fraction of the nitrate is in the particles. A pH of 2. Okay, you don't need to be neutral. Actually, if you're neutral, of course, everything is going to be in the particle phase, but most of it is already there from a pH of 3 or above. Now, if you go to a colder regime, like say in the Arctic or higher up in the atmosphere, this curve gets pushed to the left, meaning that you can have highly acidic aerosols and still significant nitrate around. So again, the thermodynamics tells us a lot of things about the partitioning. And the data support that, the thermodynamic models do a good job. So these sigmoidal curves are from the models. Of course, the scatter, the points are from observations, and you get a very good agreement. If you look at the ammonia-ammonium system, you kind of have a mirror image in the sense that when you're above a certain pH, most of the ammonia is actually in the gas phase. And when you're acidic enough, of course, most of the ammonia is in the particulate phase as ammonia. But you do not have to be neutral or below neutral to have all your ammonia in the particulate phase. You actually need to be fairly acidic for your ammonia to be mostly in the particulate phase. So again, this was another sort of revelation that made pH really important to constrain. And it really helps redefine, I guess, our concepts. So we carried out the review. It was led by Havala Pai from EPA. I was kind of a co-lead of this, and there was a big community behind a review paper that was published a few years ago in ACP. And we assembled a data set of available pHs and studies that really tried to constrain it. And it turns out that pH is acidic almost everywhere, especially in the lower troposphere. So if you go, to the Southeast US, it's on the 1 to 0, especially in the summertime. If you go to Europe, it's somewhere in between. It's a little bit less acidic because of the ammonia emissions. And again, if you go to other places like China, it could be much higher because of dust interactions as well as a lot of ammonia. But the key point is that you have a wide range of pH, and it's very important to constrain it because that determines model sensitivity to precursors. And so up until now, no one has ever actually really tested pH. And now we have a real opportunity to do that and understand if the model is giving us the right answers when it comes to partitioning for the right reason, okay? So acidity can help explain some counterintuitive things, behaviors, because aerosols in the end tend to have our buffered system, especially if you're talking about warm temperatures and ammonia is volatile. And, this was kind of a motivation of all this work was some kind of counterintuitive behavior that was observed in observations in the US during, the 90s and the early 2000s. The idea was that during the 90s, there was a lot of sulfate in the air, and there was a significant effort put to actually reduce sulfur from coal-fired power plants, essentially replacing the coal with gas, natural gas, power plants. And the expectation actually was that as sulfate went down, your acid component would go down. And then there was the fear that at some point you would start having more particulate matter because less acidity means that you might have nitrate formation. And so there was this network established to actually measure the composition of the particles over time and to really see what's going on in the system. And so what was very interesting is that over the years, sulfate went down very effectively at the cost of billions of dollars, right? And ammonia levels in, say, the Southeast US were pretty much stable or slightly higher. So the expectation was that the aerosol should have been increasingly less acidic. And the fear was that nitrate might actually start forming. So you might have an impedance in achieving low PM levels if you start having nitrate formation. But this was never really observed. And, in addition to that, the observations were showing that the aerosol was actually kind of becoming more acidic, or instead of becoming more neutralized. Imagine this, you're reducing acids, you're keeping the bases the same, and the system is not saying I'm going to actually have more neutralized aerosol. If anything, I'm actually having more ammonium bisulfate in the aerosol, which was really strange. People thought it was an artifact, but it wasn't. And in the bottom line, it turns out that thermodynamics actually told us that we're expecting this. We should have expected this. And so if you actually apply the thermodynamic approach that was mentioned before, the pHs were not really varying in the Southeast US over this, more than 10 years, 15 years time period. So even though acidity is going down, ammonia emissions are the same, your pH is about the same. Now, why is that? That's because ammonia is semi-volatile, which means that if you have ammonium sulfate around, you need to have some of that ammonia to evaporate to establish equilibrium. So if you have a lot of that stuff around, relatively speaking, a small amount of ammonia evaporates, and then you're in equilibrium. So imagine that these particles contain a lot of ammonium sulfate, maybe a little bit of bisulfate. So this was the Southeast US, say 15 years ago, 20. Well, now if you really reduce sulfate levels, you still need to reach equilibrium with a gas phase. So relatively speaking, you need to evaporate a lot more ammonia to reach that concentration required to be in equilibrium. So that means the particles that are left actually contain more sulfate than these ones. So they actually can be a little more acidic. So this volatilization is a really key component that we need to consider when we talk about acidification of particles. So thermodynamic models are really important for that. And they've been doing a great job all these years, actually. We just really didn't believe the results before we started confirming the partition. Now, I wanted to speak about this because acidity is a little bit counterintuitive if you think about beaker chemistry. There's some water around and you dump stuff inside and that affects the acidity. That is true for aerosols, only that the water that they contain varies with the aerosol mass, and it doesn't vary independently. So you really need to kind of think about how thermodynamics plays if you want to think about acidity. So with this revelation, we actually now started applying this tool to understand other aspects of the aerosol. And one favorite topic of mine is acidification of dust and the resulting dissolution of metals that occurs from that. And so one thing that's important is that if you have metals like iron, copper, and manganese, when they're exposed to acidic environments, they get dissolved. Now, usually these metals are bound to either minerals or they're in a metallic form, and so they're insoluble. But if you expose them to acidic conditions, they become solubilized. And their solubilized form actually is very bioactive. And so if these soluble things fall into the oceans, directly the solubilized metals are bioavailable. They get absorbed by the ecosystem, and then they have their impact, which could be fertilization. If you breathe these particles, the soluble parts get incorporated immediately, of course, in the epithelial, and they basically get bound, and then they cause oxidative stress that could lead to a lot of problems. And so actually measurements carried out by Ting Fang and Rodney Weber, and we collaborated, of course, in terms of predicting pH, showed indeed this effect. It turns out that measurements, at Georgia Tech, in Atlanta, there's a lot of road dust that could be very rich in these particles. In the case of urban dust, it's related to emissions from brakes. And the more acidic the particles are, the more you have solubilization of these metals. And this is very important, again, because it's related to toxicity. And in fact, if you actually carry out measurements of the size distribution of the acidifying compounds, which is sulfate, and its overlap with the dust containing the particles, it turns out that the soluble fraction of things like copper is exactly where the sulfate overlaps with the dust distribution. In other words, the sulfate provides the acidity, it drops the pH. Here, the pH for these copper-rich particles that have sulfate can be 2 or 3. That's plenty of acidity to solubilize things. And it turns out that the soluble copper is also pretty much responsible for oxidative stress. That's measured with a DTT assay, and it's linked really to the adverse health effects that are associated with breathing dust. So clearly, acidification is a very important mechanism that could explain solubilization of metals, their related toxicity, and also can explain why sulfate in the atmosphere is toxic. It's been an outstanding question for quite a bit of time now. Sulfate in the lab wasn't really toxic when it came to exposure to animals, but in the field it was. So most likely it's related to this acidification mechanism. The same mechanism that solubilizes metals, as mentioned before, can solubilize nutrients so that when the aerosol falls into the ecosystem, it's readily available for the organisms to pick up. So for example, if you look at dust, there's a lot of phosphorus in it, but it's insoluble. It's in the form of apatites. But then if you acidify the dust by exposure to pollution, for example, then the apatite gets dissolved, and the moment it falls into the ocean, it becomes amorphous phosphorus that microorganisms love to uptake. And phosphorus could be pretty much a limiting nutrient in many regions of the world. The same thing applies to iron and anything else that dust may contain. So again, acidity can play a very important part in the nutrient cycle and the impact of that, of course, on the carbon cycle. And so we carried out measurements, again, using this approach of constraining pH, but we also had an instrument that we developed that measured soluble phosphorus, and we deployed it in one of my favorite places in the world, which is Greece, and actually in the island of Crete. And, apart from being in a place that I like to be, the key point is that this region of the world receives a lot of dust. And it's from Sahara, and it mixes with pollution. So sometimes it's without pollution, and sometimes it's with pollution. So this was a perfect setup to actually measure the impact of acidification. And so, this has been published for a couple of years now, and we're also looking into more data that we analyzed. The key point is that the soluble fraction of phosphorus definitely goes up when you have aerosols that become progressively more acidified because of pollution. So if the pH drops below 2, then you have almost this big explosion of soluble phosphorus. And so when this falls into the ocean, you can actually fertilize it. And we saw the fertilization effects, and this goes back many years. It's actually one of the first papers that came out during my time at Georgia Tech. We were exploring the idea of acidification impacts on soluble iron. And we actually asked ourselves, can we see any fertilization effect in the satellite record? because there are many regions of the world that we know that really need things like soluble iron to form a bloom of phytoplankton. These are called the high nitrate, low chlorophyll regions of the world, HNLC. And it turns out that if we actually did the calculations of solubilization of iron in dust that falls into these regions, whenever the dust doesn't go through a polluted region, for example, here, you can have a deposition event. So what I'm showing you here are pictures of chlorophyll concentration. This is the magnitude here. And the idea is that this is a region of the world. This is actually off the coast of Alaska. It's a region that has a lot of nitrogen and almost no iron. So if there's something that's iron-rich that falls into the ocean, you should generate a bloom. Well, you do have dust events that get transported, Gobi Desert dust, and falls into these regions, and you don't see any bloom whatsoever, even though you can have a lot of iron in this dust. It's insoluble, so it doesn't stay long enough to be absorbed, so it doesn't cause a bloom. But if another dust plume goes through a polluted region, say Beijing, and then gets transported and falls in this region after the deposition, and exactly after a certain period of time that's required, you see the dust bloom. The phytoplankton bloom. So in other words, when we predict that there should be a lot of soluble iron, you actually do see phytoplankton bloom. And this was a really remarkable result that we thought was definitely worthy of publishing. And it shows that acidity together with dust can really have a fertilizing effect in the oceans beyond, what we would normally expect. And actually, you can have so much of a fertilization effect that it may actually affect the oxygen levels throughout the whole Pacific. So this is a study that happened many years later. And the idea, excuse me, I'm recovering from a little bit of a flu. And the idea is that the pollution that interacts with dust deposits in this region of the ocean. Not all of the iron gets absorbed because there's too much of it. And it gets transported to other regions of the world that actually may need the iron. And you may actually cause a eutrophication of the tropics. And this is what's been going on for the last few decades. It's been observed that the oxygen levels in the subsurface tropical Pacific is going down a lot, actually. And it's counter to what we were expecting from global warming. It turns out that it may be this fertilization effect at large scale, just massive deposition of soluble iron through interaction of dust with pollution and transport, and essentially affecting the productivity at the whole Pacific Basin scale. And actually, we can measure oxygen decrease, and it's consistent with modeling, and the patterns of oxygen decrease is also consistent with modeling with this mechanism in mind. So again, it's one other impact that we have on the ecosystems that we really need to take under consideration. And it's all related to acidity, okay? Now, one more thing, going back to the partitioning, remember that the amount of stuff that goes into the particle phase depends on the pH. So if you have a high pH, that means that a lot of the nitrogen will go to the particles, little ammonia would be in the particles, relatively speaking, and vice versa if you're acidic. You will have a lot of ammonia in the particulate phase and very little nitrate. So keeping this in mind, we can actually start thinking how we can use this to understand particle sensitivity. And just to give you an idea, you can actually express the theory, and I won't go into the details, but the key point is that this partitioning fraction, you can show it depends on pH, so the hydronium concentration, and also the liquid water content. And that makes sense, right? The more water you have, the more you tend to dissolve stuff, so you push partition to the aerosol phase. And you can show that the theory predicts this partitioning fraction really well in terms of these two parameters, H plus and liquid water content. And depending on the conditions of temperature and liquid water content, you get these beautiful partitioning curves, which are backed by observations. So if we actually do an analysis on these curves and ask ourselves, when does particulate matter really respond to changes in ammonia and nitrate levels? We can actually come up with some really neat and simple conclusions. So here are these partitioning curves. This is for nitrate. I'm showing you sort of this equation. Don't worry about these psi and phi, or psi and phi as I call in Greek, parameters. These are related to thermodynamic properties like activity coefficients, etc. The key point is that this partitioning depends on pH and liquid water, and you get these beautiful curves. Now, if you analyze these, you can actually say, if my partitioning fraction is above, say, 0.1, that means that the aerosol gets a good amount of partitioning from the gas phase. That means that aerosol is sensitive to a precursor that we're looking at, ammonia or nitric acid. At the same time, if you're actually not above 0.1, that means your particles are insensitive. So you can come up with a very nice definition of characteristic pH for these two curves and say that if my pH is below this level, then I'm sensitive to ammonia because my partitioning fraction is high. But I'm not sensitive to nitric acid because its partitioning fraction is low. Vice versa, if I'm above 3, I'm sensitive to nitric acid, but not ammonia. And if I'm between these two pHs, I'm sensitive to both. So automatically, just by looking at the pH for these partitioning curves, I know exactly if I'm sensitive to one or the other. Now, this partitioning curve is calculated for a given level of liquid water. If I now start varying the liquid water, I actually get a nice map that tells us these characteristic pHs, and we can define essentially where we are in terms of sensitivity. In other words, if I have liquid water and pH, I can place myself on this graph and know exactly if I'm sensitive to nitric acid, to both ammonia and nitric acid, or ammonia. Or actually, I could be insensitive to both. And so this is important because it tells us essentially what PM is responding to. And so we took this map approach, and we took data from various sites, and we started seeing consistent pictures with what we know. So taking Netherlands data, we know Netherlands has a very high ammonia concentrations, and it's very sensitive to nitrate levels, nitric acid levels. So effectively, if you plot the data, indeed you're in the nitric acid sensitive region. Sometimes you're in the both, but for most, at least for this data set, which covers a year of data, you're mostly in the nitric acid sensitivity regime. If you're in the Southeast US, where I lived many years of my life, we're in the ammonia sensitive region. In other words, if you increase ammonia emissions from agriculture activities or whatever, then that would increase automatically PM levels. So nitric acid levels actually are not that important. And that's why, even though the sulfate went down, we never saw nitrate forming in the Southeast US. You're just not in that part of the map. And we can actually now take simulations of air quality that have these thermodynamic models in them and figure out as a function of location where we are in terms of sensitivity. So, I live in Europe now. I spend a lot of time in Greece. Sometimes I'm in Switzerland, or I go further up north. And you can see a huge gradient of pH and liquid water in Europe. And again, you can transition all the regimes depending on where you are. So this is really nice because this tells you that the emissions policy for PM is region dependent. And using map approaches and good data can actually get you a lot of the conclusions you need. It also gives you the data you need to evaluate the models. If you get the pH right in the models, then the sensitivity in the models is right. And you know that the answers you get are right for the right reason. If your pH is off by a unit, then you may be on the other side of the sensitivity curve, and you may get totally wrong responses to emissions. And so you need to do something in your model to fix the pH and get it right. So again, this introduces a new way of evaluating models, which is very important. Okay. Now I'm going to go a little bit faster. I just want to point out the last aspect of partitioning and pH. It's also important for nitrogen deposition. Okay. And this is because if you're in the gas phase or in the particulate phase, your lifetime is very different. So nitrogen in the gas phase tends to last very little. It tends to deposit very quickly. And so if your nitrate is in nitric acid, it tends to deposit locally. If it's in the aerosol phase, it can stay for up to 10 times longer, which means that it can also accumulate in the boundary layer and cause a huge nitrogen event, a nitrate event, and also transport very long distances before it falls off. So it has important implications on the deposition. And so, again, at the heart of all this is acidity, pH. So let's take these curves again and look at the partitioning fraction. And here we're going to say that if you're 90% partitioning in the aerosol phase, then you're kind of mostly in the aerosol phase So that nitrogen species will deposit slowly because it's in the aerosol phase. And vice versa, if a good fraction is in the gas phase, then that very fast deposition dominates, and essentially you talk about fast deposition of that species. So again, you have your characteristic pHs, and you can have, if you're acidic, ammonia deposits slowly and nitrate deposits quickly. If you're not acidic enough, ammonia deposits quickly because it's mostly in the gas phase, and nitrate deposits slowly because it's in the aerosol phase. And then in between, both can deposit slowly so they can accumulate in the boundary layer. And so again, you have a map for the dry deposition velocities. And depending on your value of pH and liquid water content, you can be in this region. So once more, you can figure out what's going on with ambient data. Going Netherlands now, you actually have for large parts of the year, slow deposition of nitrate. And during these times, that's when nitrate in the boundary layer accumulates and becomes very high. So it's not just being sensitive, it's also being in a slow deposition regime that really accelerates these nitrogen-rich events. And this is definitely something that's strongly relevant for many places in India. And you can also do the same thing for other semi-volatile acids like hydrogen chloride and organic acid. So this is a general approach that can actually be very useful. In the Southeast US, things deposit quickly, and generally speaking, except if you're very acidic, then ammonia can be slow deposition and get transported. Okay. And again, you can evaluate models, and you can also see what the models are telling you what's going to happen in the future. And so just to give you a quick heads up, this is a paper that was published a little over a year ago with a global model. And the orange area are places where you have slow nitrate deposition. So right now, Europe tends to have nitrate in it, in the aerosol, a lot of it actually. And the same goes to Southeast Asia. But in the future, when we have changing emissions, you actually switch acidity regime, and then you're on the other side of the map. And it turns out that you might actually not have nitrate anymore. So you might have a very quick transition where the air all of a sudden loses its nitrate. And again, that would be a good thing for air quality because that means less PM levels. So again, this is all important to consider. And it's very nice because you can interpret the simulations and they tell you the sensitivity regime. Hence, you have a much better understanding of what's going on and why. Finally, I'd like to give a heads up. We're now in Switzerland leading a nitrogen initiative to understand the nitrogen cycle. And so all these concepts that we've discussed up to now are very important for the initiative, at least the atmospheric side. It's a collaboration between 5 institutions, EPFL, the Paul Scherrer Institute, WSL, ETH Zurich, and ERWAG. So these are all part of what's known as the ETH domain in Switzerland. And we're all working together to understand how the energy transition will affect the nitrogen cycle, the concentration of these species, the acidity of the atmosphere, nitrate in the groundwater. And so if you're interested, please tune in. We have a seminar series that's about once a month. We have a Twitter account that we post all these things. Please go ahead and join if you want. Anyone can join. And you can also go to this link to check the recordings of past seminars. So some take-home messages. Hopefully I didn't take too long. Aerosol acidity profoundly impacts processes that relate to pretty much everything that aerosols do. There are very few things that will not directly or indirectly be affected by acidity. But for the longest of time, we actually were blind to the exact levels of acidity that we had in the aerosol. The models were predicting them, but we weren't taking those predictions seriously, which always was a funny thing for me, because we always use these models for predictions and we trusted them. But anyways, I think we come into terms that the models are actually doing a fairly good job in predicting pH, and we can actually apply thermodynamic models to infer the pH of the aerosol and get pretty good assessments if we actually can reproduce the partitioning that they predict. So if you have a good data set and you reproduce the partitioning, and you're in conditions where the thermodynamic equilibrium approximation works, then there's a good chance, very good chance that your pH levels are well predicted. And all the evidence to date on solubilization of metals, the impacts of acidification, falls in line with the pH levels that are predicted. So I think we can say that we have a good idea of pH for a lot of the aerosol we find in the atmosphere. Because of that, we can now use pH and liquid water as ways to really look into the aerosol and evaluate models in ways that we've never done that before. And this is important because if you get the pH right, the models have sensitivity to precursors that are correct. And they would give you predictions that are consistent with the observations if you have the emissions right. So you get the right answer for the right reason, so to speak. That's very important. And we can also interpret data and get insights on the sensitivity of PM to the emissions, as well as the nitrogen deposition, the dry deposition rates. And that carries, of course, important implications for haze events because of the accumulation if you have slow deposition in the boundary layer, but also it's important for nutrient transport and deposition far away from the source. We still need, of course, a lot of work to directly determine pH in particles, and there are emerging techniques. So hopefully in the next few years, we will be able to directly figure out the pH of single particles, and that will be another sort of transformation in our ability to understand and predict things. But at least for now, we have a good understanding of pH. So with that, I'd like to thank my research groups in Switzerland and Greece and former Georgia Tech groups. It's been a wonderful, experience over the last few years on this topic of pH. We're very excited about it. We still want to explore a lot of things. I would like to thank my collaborators. A lot of this work is done in collaboration with other groups. So Rodney Weber, first of all, from Georgia Tech, and Ted Russell. Maria Kanakidu in terms of the ecosystem work, and Nikos Michalopoulos. Spiros Pandis when it comes to some work related to the sensitivity. Mike Crum and Taka Ito when it comes to the geochemical implications of all this. I also like to thank my family because without them, of course, nothing would happen. And I also thank you for your time, and hopefully we have some time left for some questions.
Thank you. Thank you so much for such a wonderful talk. Many complicated things you have explained in a very lucid manner. I'm sure people could follow, but people may have many questions. So now we can have some questions. So what
Yes.
I would request the audience that please raise your hand and I will call you and you can directly interact. In case if you are not able to speak because of some issue, then you can type the question in the chat box and I will read it out. So first people can raise the hand. So, okay, until people are raising, somebody has written it in the chat box. So let me read out the question for you. So what will be the role of complex organic acids in changing pH regimes in the presence of dust aerosols?
Yes, so organic acids can definitely introduce acidity, especially acids like oxalic acid. It's an acid that is not as volatile compared to, say, formic and acetic, but it's also quite strong. So if you have enough of it around, it can actually really contribute to acidity. And so we've done calculations of that. You need to have a certain amount of them. When it comes to other types of acids, and if you're in the dust sort of regime, again, it's a matter of how much of this acid you have compared to the inorganics. They can compete, but again, you need to have relatively high amounts. So that's the only limitation really here. So maybe in the future, when we will have much less sulfate around, that role of the organic acids will become much more important. But yes, this is definitely an important question, and that's, again, research that needs to be carried out and figured out in a way that could be easily implemented in models.
Okay, thank you. So until I see another raised hand, let me ask you something which I was thinking about when I was looking the talk. So what I understand that especially when we talk about the effect of aerosols on health, or when we are talking about the deposition of nutrients through the atmosphere to ocean or lakes and all. So especially for the health effect. So if we are in some urban areas and if we have fresh aerosols, so they are expected to be less toxic compared to more time they spend in the atmosphere, because once they spend more time, they interact more with the acidic component, and then they become more toxic because of the solubility and all, then they become more toxic. So what do you say about it?
I completely agree. And that's the idea, that the more these particles reside, the more toxic they become, because your content, your soluble iron and other metal content goes up. So yes, that's exactly right.
Okay.
And also its ability to fertilize goes
Yeah.
up as well.
Yeah. Yeah. Another thing I was thinking is when we are talking about different particles, we know that different particles have different hygroscopicity. Say, for example, when we have ammonium sulfate, they will attract water and liquid water content of those particles. When we are talking in the atmosphere, once we collect it, they are all together. But when they are in the atmosphere, all particles are individual. As we understand, means with transport they become mixed particle, but means initially they are individual particles. So somewhere individual particle when we are talking about, somewhere the pH may be even lower than what you are showing, and for some other particle it may be higher because they are not in contact. So because
Mixing.
yeah.
So that is definitely a very important question. And whenever you apply these thermodynamic approaches, you assume internal mixing, or at least you need to consider some kind of internal mixing to get a reasonable answer. And I think, again, being able to show that your partitioning is right. So that's why it's important to have the gas phase and the particulate phase concentration of these species. If you have the partitioning reproduced, that is a very strong indication that your internal mixing doesn't affect the bulk of the aerosol. But as you go to larger and larger sizes, that external mixing will be increased. And at some point, you just need to say, okay, I don't really know what's going on with the acidity of the super large particles. And that really requires new measurement techniques to help constrain things. But when it comes to PM1, you can make a good assumption that you're in thermodynamic equilibrium. It depends how close you are to the sources. But again, after you go somewhat far away, particles do tend to internally mix. And at least the bulk of the data we have at hand supports that the partitioning is reproduced, which means that the pH is representative of the particles. But yeah, if you have high degrees of external mixing, then you will have particles that have a higher and other particles that will have a lower pH. But they will quickly equilibrate because mass transfer is pretty fast if they're small enough.
Okay, thank you. Okay, so now I saw another question in the chat box. It is little
Yeah,
long.
there are a couple of questions. Great.
Yeah, it is little long. So should I read? You can also see that. So it
Yeah, I
is by
can see it,
Chandrima.
and I can go ahead and answer.
Yeah.
So one question, which is short, says, does the Sodopia contain any option to include organic acids for pH and liquid water calculation? So organic acids, no. What is Sodopia? The current version, it considers the hygroscopicity of the organic fraction, so you can calculate its liquid water content. So unless if the organic fraction is a huge part of the aerosol, and especially organic acids, you can actually do an offline calculation of extra pH from the organic acids that may be present. And, that's one thing that we're considering to do. But, other models do consider acid partitioning, like, for example, EAIM has oxalic acid. And calculations that we've done to compare the two models, they still agree quite a bit, unless if you're talking about huge oxalic acid fractions that you don't often see in the atmosphere. So bottom line is, I don't think that we need, at this point, to have a lot of organic acids in the partitioning. And there are ways to kind of couple isotopia with some kind of offline calculation to get an extra acidification. But that definitely is something that we should consider in the future.
But I feel that inorganic acids are much strong compared to organic acid. So even if there is the effect of organic acid, it should not be significant. That is what I feel.
Yeah, you need to have a lot of organic acid and very little of the inorganic to say that the organic really starts dominating the H+.
Yeah.
And unless we reach that situation, the inorganic fraction dominates the pH. That's why we get partitioning so well agreed with observations in the ambient data, which have organic acids. Okay, so one more question is, I have, in the case of reverse mode isotopia, there's a huge discrepancy in the real gas phase estimated by the model. And the reason why reverse mode can have a large discrepancy is because when you measure aerosol composition, there's uncertainty. And so if you have a 10% uncertainty in your ammonium and you're a pH that's closer to 5 or 7, that can translate to a huge uncertainty in pH, because you're talking about the fourth or fifth digit that you need to have right in the measurements. And so if you have that uncertainty, so that can predict a gas phase concentration that's very large, which of course is not what you observe. But that's a result of the uncertainty of the measurement and the way that the problem is formulated that tends to magnify those uncertainties. So if you get in touch with me, I can forward you a paper that describes that in much more detail. But that's why we never use reverse mode to get pH calculations. We always use forward mode, which is much more stable.
So I would suggest Chandrima to contact you for that.
Yeah.
Okay.
Absolutely.
So yeah. So anyone else wish to ask?
I guess people are leaving now.
Yeah.
But,
So yeah.
but
So
still, there are many people online.
yeah. So I think Ms. Omsur wanted to ask. They asked. So let me go to the last part of the talk. That is vote of thanks. So that is my present duty. So first of all, I wish to thank you, Professor Nenes, for
So much
accepting my
again,
request.
everybody. Thank you so
And it
much.
was, Ms. I was really, I'm very humbled that you accepted my request and you gave this talk from your busy schedule.
It's
And then I also wish to thank our BARC team who actually do all the work. So they make the flyers, they make all kind of arrangements for the YouTube live and Zoom and all. So thank you, BRC team. And other than that, means it is any talk is incomplete if we don't have audience. So I wish to thank all the audience for coming and listening the talk. And whomsoever want to see it again, it will be available on YouTube channel. And who could not attend the talk, we will post it further, and they can always see the talk. It will be available on YouTube. And once again, thank you again, Professor Nenes.
Thank you so much.
With this, yeah. So maybe we
Professor
can,
Astaki.
yeah. Thank you. Thank you so much. Yeah.
Bye-bye, everybody.
Bye.
Cool.